Started here and sharing the screen. We started last time on the chapter on the Fukushima accident, and we are giving it, of course, a great emphasis. A reminder that our final would be on the last day of classes, so just be aware of it. The last time we described the phenomenology of the accident, and today what we want to do is learn some of the features that we can infer for future improved designs. We try to identify the three main causes of severe accidents beyond the design basis accident for nuclear power plants, which are equipment failures, faulty designs, as well as human errors. The Chernobyl accident added to that list the possibility of a natural phenomenon also causing us trouble. You could see here the effect that basically the shield or the shield that was built to prevent the water from a tsunami coming in from a hurricane was totally overwhelmed. You could see here, these are some fuel tanks here. The water comes in this area. You could see those vehicles here. They start floating. The water rises and almost buries totally the fuel tanks and finds its way to the basement of the plant. And that was totally unexpected in the design. It was a design flaw from the perspective that they built the plant very close to the water level. They went there and flattened the ground. After the water flooded the basement where some of the safety equipment was, you could see it retreated back to the ocean, but the water remained at the bottom of the plant itself. And at the bottom of the plant, you find that the safety equipment that was of concern in that case is that particular turbine. That turbine was getting steam from the main steam line. You could see here, if you follow it, this is a valve here. It gets the steam from the main steam line, and then it rotated a pump. And that pump would provide fresh water in the case of an accident. The accident that happened, in fact, from what's called in boiling water reactors, the condensate storage tank. We listed it as one of the engineer safety features, not only from the condensate storage tank, but also from the pressure suppression pool at the bottom of the reactor building. Now, I'll show you in a moment that pump and that turbine were in the basement of the reactor, and they were both flooded. As being flooded, electricity and water don't go together, so that main safety feature here was not available to us for as designed to deal with the decay heat in general. The main steam valves played a role in that. The steam valves there open up against the pressure, as you could see, of springs here to get the atmosphere of the containment released to the environment in the case of a release of hydrogen. And the hydrogen release, as we identified it, would come in from steam at very high temperature from the core spray system in boiling water reactors interacting with a metal. The metal in that case is a cladding, the zirconium. A flaw in the design that we can suggest is that the pressure in the containment was high enough so that those pressure, the pressure in the containment was so high that those valves were not able to open up and relieve the containment atmosphere to the environment. In that case, hydrogen accumulated, and we ended up with the risk of a hydrogen explosion. You could see here at some stage in the accident, in one of the reactors, I think number 2 unit, you could see the steam trying to escape from the top, whereas this one did not have steam escaping from the top. Another flaw in the design was that those stacks here or chimneys were meant to release, in fact, the hydrogen in case of an accident, but they were some kind of connected from one reactor unit to the other. So they had only 2 stacks instead of 4, the 4 units that were involved in the accident. You could see here, steam is being released, but this is an actual picture. And in that case, what is being released really was burning. And that what was burning is, of course, the hydrogen being released from the containment structure. At some point, you could see here that in the dry well, sensors that measure the pressure have increased from 0.4 megapascal here all the way to almost double, 0.8 megapascal. And this is attributed to the hydrogen being very reactive, causing some kind of an accident. This is the position of the steam relief valves in the containment structure. They all failed to operate to vent the hydrogen and steam pressure from the containment. That was a flaw in the design. The designers of those relief valves did not realize or did not take into account that the steam released in the containment itself, of course, would create pressure that prevented those steam valves from operating. So these are some of the design flaws. Eventually, you'll find that the operators were really very smart, so they went and used the really manually operated safety relief valves, and they were able to relieve the pressure from the containment itself. So these are some of those. This is non-manually operated relief valve, and this one did not operate, but the manually operated relief valves were made to operate. In the design of what's called the light bulb design of the BWR of the units built by Toshiba and General Electric in that case were such that they had 3 levels of containment relief valves, containment pressures. Class S would be in the containment structure itself around the pressure vessel, as well as in the pressure suppression pool. This would be a region of pressure to be relieved. Class B is another region in the plant itself, and Class C would be on the side of the turbine and the electrical plant. This is a description of that safety relief valve design, and those springs here simply could not overcome the pressure built up by steam in the containment structure and failed to operate. And this is how those valves really look like as a picture. So second design flaw, the first design flaw was that they built the plant by flattening the ground very close to the water level. And in that case, the effect of the wave from the tsunami was simply led to flooding. This is a picture here of the different units after the accident. Remember that the plant had 6 units. Reactor number 1, you could see that the roof was gone there. Reactor number 2 damaged inside, but the roof, the structure of the containment outside was still there. Reactor 3 totally destroyed. Reactor 4 was not operating. They had the core outside of the fuel outside the core, but it had, you see here, the stack and that stack here, that had the stack from the other units diverted towards it just to save some money. Instead of having 4 independent systems for the release of the hydrogen, they had only 2 systems. So the hydrogen moved from one unit to the unit that was shut down and caused a monumental fire. The fire led to explosions. Some explosions are identified as being hydrogen explosions, but I'll show you that one of them, particularly in unit number 3, was more closer to being a steam explosion. In fact, initially a criticality accident, then turned into a steam explosion from the point that I'm going to try to make. Notice that units 5 and 6 were not in operation, and they were not affected whatsoever by the accident. Why? You could see it immediately here from that graph here, as those 4 units were planted or built very close to the sea water level. They're cooled by seawater. Those 2 were built on high ground, were not affected from the accident. So we identify as a design flaw that they were built too close to the water level. This would be the turbine plants here, 1, 2, and for unit 1, 2, 3, and 4. And you could see that there has been some damage by the reactor catching fire and the hydrogen explosions, of course, affecting the roofs of the building. This is the plant before the accident. This is unit number 1, unit number 2, 3, and 4. Remember that 5 and 6 were not in operation. Here they are, safe and not affected by whatsoever by the accident. This is the way it looks after the accident. Number 1, the roof is totally gone. Number 2, not much affected. The containment structure remained there. But number 3 was damaged beyond any kind of imagination here, as well as number 4. And number 4 had the fuel outside the core, even though it got a fire. So you could see the damage that happened from the fires and the explosions also affected here, as you could see, all the equipment around the plant itself, and that we had 2 stacks instead of 4 stacks. So in that case, if you have 2 stacks ventilating 4 units, you'll find that we have a situation of what we considered when we talked about fault tree analysis, like in the Browns Ferry accident, the cabling and the steam lines were some kind of interconnected. We call that a common mode failure. So that is a very, very typical common mode failure. They had a stack for those 2 plants. The hydrogen was directed from this one that was operating to the one that was not operating, and caused a fire there, probably in the fuel storage pool. This is a picture from above, from an airplane, obviously, for the units number 5 and 6 here, unaffected by the accident, and then units 3 and 4 and 5 and 6 here before the fires destroyed units 3 and 4. This is 1, 2, 3, 4, and this is 5 and 6 right there. So it ended up as a fire. And this is another picture of the fire from above. Some people suggest that the fire was in the fuel storage pools. In nuclear reactors, after you use the fuel, you store it for as long as you can in fuel storage pools. And they have to be cooled because they continue generating decay heat for a long period of time, and they have to be cooled. If they're not cooled, and apparently this is what happened there, then that fuel can catch fire, and then of course radioactivity would be released to the environment in that case. This is going from right to left. Unit number 1, the roof destroyed. Number 2, destroyed inside, but not the roof. Number 3 had a fire. Number 4 hadn't caught fire yet, but the diversion of the hydrogen into the same stack from 3 to 4 caused eventually a fire in number 4. And that is on March 15, 2001. As of course, the cores were not cooled, the decay heat continued to be generating without cooling. The people in charge noticed that immediately. So I think they sought help from the United States Navy. It had an aircraft carrier there positioned near the site. So you could use here, they used helicopters that brought in water from the ocean and started pouring it on top of the reactor to extinguish the fire. Later on, the operators from Japan were able to bring in firefighting equipment, pumpers, and you could see here they use really firefighting equipment, and they used seawater in that case, so that basically damaged beyond repair the cores of the reactors, because seawater would be causing, of course, lots of corrosions. These are a picture of the heroic work that was done there with all those firefighting equipment doing it. Here you see that they are trying to direct the pumpers into the reactor building, and it was actually really what we designate as a station blackout. Station blackout refers to the situation, and try to remember that name. And in fact, I can give you a paper to read about a station blackout situation. We did it for one plant in New Jersey. That is the Hope Creek plant. And you can recover from station blackout. In a station blackout, you lose both the power that is being produced by the plant, as well as power that nuclear power plants, as a contingency measure, are connected to the grid system. And it turns out that the tsunami, or the earthquake in that case, not the tsunami, but the earthquake, damaged a switch yard that would have connected the plant to the grid. So you could see here, this is a control room, totally blackened out. In a normal blackout accident in a boiling water reactor, since you would boil the water, the moderation of the neutrons would be stopped, and the system could shut itself off. But of course, there were other consequences from the safety equipment not being able to operate because it was flooded in the basement of the reactor. Eventually, the operators were very smart, so they thought getting batteries. There is a battery bank, in fact, that was used as a safety backup system, but it was also flooded. It was in the basement. And so they got batteries from the United States Navy. Well, those batteries were 2-volt batteries. They failed in providing power to the control room. So the operators there were very smart. They went to their own cars and disconnected the 12-volt batteries. Eventually, they started getting power into the control room and recovered from the total station blackout. And they recovered the power basically in Unit 1 and 2, and the control room of Unit 2, the hanging ceiling tiles you could see here resulted from the earthquake. So it was a very, very significant earthquake, and it was a heroic type of very smart operation that it didn't get worse. As we know, though, Japan is part of close to the ring of fire around the Pacific Ocean. Volcanic eruptions and earthquakes are very common. The Japanese live in an environment where basically earthquakes are very common. So their power plants are designed to withstand those earthquakes. And every once in a while, when the earthquake happens, some damage happens to some of the equipment. So that shows us some equipment damage. The earthquake ground subsidence, meaning that the ground fell down around a light oil storage tank. And that has a capacity of 30,000 to 40,000 gallons. So that was in 1979. You'll find that some earthquakes also caused the piping. So this is the result of an earthquake that is connected, in fact, in an earthquake fashion so that it doesn't buckle, but it did buckle here. So in that case, plants are shut down when earthquake happen, and some repairs is always needed. A vulnerable kind of part of the plant is the transformers. I'll show the result later on. So this is in fact, how the plant looked like looking from the ocean, from this direction. And you'll find units 1, 2, 3, 4 before the accident, and the 2 stacks there. And what I wanted to show you here, and I did follow it on Google Earth. You can do that. The same thing, that the plant is connected here. Do you see that line here? It goes to power lines to a switch yard 8 kilometers away from the plant that is supposed to provide power to the plant in case, say, the power from the plant itself is not available to run the safety equipment and the control systems. but apparently the switch yard at 8 kilometers away was affected by the earthquake. So in that case, it was a station blackout. No power at the station and no power from the grid. Now, coming back to this flooding situation, many people made a mistake during the analysis of the accident. They took that units here, number 32. 32 is basically transformers, a switch yard at the ground level, and said, oh, these are the emergency core cooling diesel generator. That was not the case. These are a switch yard. The emergency diesel generators are situated right here on a high level in the plant itself. So they were basically, they didn't have available to them enough fuel to run. They ran for a short period of time only. And that turbine that I have shown you, running a pump that would provide cooling from the condensate storage tank, is situated there, here, and here at the bottom of the plant itself. Now look here, this is the ground level in drafting. You move here all the way here, and these are definitely underwater. And this is a design that is even more advanced than the Fukushima plants. That is not the light bulb design, even though the pressure suppression pool is below the core here. But if you read here the 17 on the legend, this is the steam turbine and the pump, and they were definitely, no way they were underwater. So in that case, if we have boiling water reactors or pressurized water reactors with equipment in a region where we can get flooding, now this is a new type of an accident that we have to take into consideration, both in the design and the operation of existing nuclear power plants. As I said, this is the advanced boiling water reactor. The Fukushima reactors were older designs, so even in new designs, we have to take that now into account. As I suggested, earthquakes have been happening in Japan. This is another situation where the earthquake caused a fire in one of the transformers, and it was caused by an earthquake in 1979. Okay, so we identified the accident as a station blackout accident. There are many designs of boiling water reactors operating in Japan. As you know, that they all were shut down after the accident, and safety reviews were done on all of them. Japan was forced to import large quantity of natural gas to provide electricity to its large cities and industry, like Tokyo, for instance. Safety reviews were done, and they discovered that they can restart those plants. So one by one, after safety reviews, they are restarting them. But the designs are very old designs. You could see these are all designs of Fukushima, Daiichi 1, 2, 3, 4, 5, and 6, are all of them built by General Electric and Toshiba. Toshiba, Hitachi built one of them, Toshiba again, General Electric and Toshiba. So these are the two architect engineers that have been building those plants. One of them in particular had an interesting type of fuel that was called the mixed oxide, and it was being experimented on, and some people suggest that that type of a fuel was very reactive and may have caught fire in the unit number 4. Let me see. So you could see here, these are all the different designs, Mark 1, Mark 2, and this is at Kariwa 6 and 7. This is the advanced boiling water reactor that I have shown here, the advanced boiling water reactor. These are new units, and of course, there should be awareness of the possibility of the flooding accident in general. As I suggested, explanation of that fuel, the fires that happened in unit number 4, that was in actually unit number 3, is that it had that mixed oxide fuel. Mixed oxide is a combination of uranium dioxide and plutonium dioxide. You get the plutonium dioxide after you reprocess the fuel, in that case, you do not throw away some valuable fissile material, the plutonium in that case. However, we know that it is highly reactive, it can catch fire, and it seems that something may have happened that we are not aware of fully. This is the description of the decay heat removal system. As I suggested that the longer you operate the plant in the chapter on decay heat systems, and you have a small program that people have used, in fact, at the time of the accident to calculate that decay heat, you could see that as you operate a reactor for 10 years, you can have basically a power, decay power that can be very significant. This is a natural logarithm of power, but it decreases really rapidly within a day or 2 days. If you are able to cool the plant, that decay heat simply disappears. But the energy that you build up, if you do not extract the heat, can be significant to cause great damage to the plant. I show here the equation that we described separately in the chapter on decay heat. And I show you again here that within immediately after the accident, so this is assuming the power, decay heat power relative to the fission power is about 6%. So if you have a plant that has 3,000 megawatt thermal of power, 6% would be 6 multiplied by 3, let us say about 180 megawatt thermal of power at basically immediately 1 second after the accident. Notice how the decay heat decreases very rapidly. If you recalculate the values 1 minute after shutdown, oh, that 6% now is halved to 3%, and within even a longer period of time, I think I'm using here 1 day, it's only 0.45% of the fission power. So you have to survive really a few hours with the decay heat, and for this reason, the decay heat has been the common feature that caused 3 major accidents that we had to deal with in the nuclear industry. It was in the 3 Mile Island, it was in the Fukushima, and it was in the Chernobyl accident. That's why the new designs of nuclear power plants emphasize ways of dealing with that decay heat. One solution is to progress from using solid fuels. In that case, as you know, the fission products remain in the fuel, and then the plant is refueled every year or a year and a half. If you use a liquid fuel like a molten salt, you can continuously extract the fission products, and that accident would simply disappear from the annals of nuclear energy generation. Unfortunately, it didn't happen, even though in the electrical generation business in general, initially steam boilers used coal as a solid, but it was discovered by, in fact, Winston Churchill in the First World War that liquid petroleum was discovered in the Middle East, and he switched all the power supplies to the British fleet from coal, a solid, into a liquid. Unfortunately, the switch or the evolution from solid to a liquid in the nuclear industry did not happen because of basically bureaucratic kind of inertia. Within a week, I didn't show these calculations earlier when we studied the decay heat. You only have about 0.24% of the decay heat. So if you really are able to cool the plant for 2 days, maybe 48 hours, you get into a safe configuration. We listed before the engineered safety features of the boiling water reactor. And again, I'll show them here to you. You get the core, and you have the pressure suppression pool. This is not a good design because in that case, you need active systems to cool the core by getting water from the pressure suppression pool in the shape of a toroid at the bottom of the plant itself, as well from the condensate storage tank. It's not shown here. A better position for that pressure suppression pool would be obviously above the core, where right now they have the fuel storage pond. Notice that the pressure vessel is contained inside that concrete inverted light bulb kind of a design. And on the top, you have a concrete shield plug. We'll come back to that concrete shield plug. I'll show it to you that under the suspicion of a steam explosion, that plug basically flew up in the air to maybe 200 or 300 feet up in the air. How would that steam explosion could have happened? That area under the core of a boiling water reactors have the inlet for the control rod. They come in from the bottom. Why? Because for two reasons. We have drying equipment at the top of the pressure vessel in the boiling water reactor. There is no room there, like in PWR, to insert the control rods from the top. And second, the boiling creates more bubbles or void near the top of the reactor. So the moderation of the neutrons and hence the power is lower at the top of the core than near the bottom. And if you want to control any condition, you control it where it reaches a maximum. That's the reason for the control rods to come in from the bottom. This area is called the dry well. So you don't have any water there. You see the water is surrounding the core. If it were up, as I suggested, then you can have natural circulation to cool the core rather than having to run pumps and quench the steam that would be produced in an accident in the pressure suppression pool. But if this area is filled with water, and then you end up in a situation where the core melts, it will find ways of leaking through the control rod inlets. And if there is water there, we studied the steam explosions before, you can have a monumental interaction between the water, the corium material, the molten fuel, and water there in the area under the core. And in fact, this is what TEPCO tells us, suggests that part of the accident. They show here in the diagram the core melting in unit number 1. They show that the core melted up, and they show the molten core material. They do not show it interacting with water here that may have leaked into the dry well. It was not a dry well anymore. So the assumption here is that a steam explosion happened. It's easy for the liquid to melt a seal of graphite that surrounds the control rods coming from the bottom of the core, and a steam explosion becomes possible. Another modeling from TEPCO, the Tokyo Electric Power Company, they show us here that the whole core in unit number 1, at least that's what they did simulations for, would have melted and embedded itself in the concrete structure. Now, if it were dry, well, that looks very much like just a pure meltdown of the core. The molten material would deposit itself here in the concrete. But if there is water there, if there was water, then definitely a steam explosion would have happened, and the lids there on the top would have been thrown up to the sky. And that's exactly what happened here. The simulation by TEPCO, they show us a simulation where the core, in fact, you could see here, these are videos that they issued, that they acknowledge that the core melted, the cold molten material went through the control rod inlets. These are the control rods here. And they suggest it deposited itself at the bottom of the core and stayed there. Now let us see what happened in the observations of the accident. This is what they say: the core melted down. Let us look at the safety analysis report of a typical Mark I design, which is a light bulb design there. This is a pressure suppression pool here. This is a dry well under the core. So in the actual design, you would see that the core would have melted down into that area of what's called the dry well. And if you look at from the side, this is again should be a dry area. Notice here, this is the ground level. And if you look at the ground level here and you look at the equipment all below the water level that was flooded. All that area was flooded, where basically switch boards of and that particular pump that is being driven by a turbine were located. So in that case, lots of the safety equipment in the basement here were flooded because they built the plant too close to the water level, and just maybe they didn't have any other area, so they flattened the ground and built it very close to the water level. This is another picture of the again, look here, this is the ground level here. Here it is, this here. All that area here, if you look very carefully, you'll find that here, for instance, look, we can read this one, battery room. These are batteries that were supplied as a safety feature to provide power to the control room in the case of an accident. Well, these are now those batteries in the basement shown by a gentleman there. These are a switchboard there, switching equipment in the basement that you could see here. It was filled with water, and algae from the water are remaining there. So all that safety equipment became unavailable with the water flooding it on May 6, 2016. This is when that picture was taken. Of course, because of the meltdown in the core, the fission products from the fuel were released. And people, of course, identify the iodine 132, but in fact, we are smarter here. We are studying safety. It comes in from an isotope of tellurium. The isotope that is released in a reactor accident, if the fission products are released, is beryllium 132. That's the first isotope that is detected in the case of a reactor accident. Tellurium, though, decays into iodine 132, emits a negative electron, a gamma photon, and anti-neutrino. So you'll find that, again, we have two tables here, like we separated there in the chapter on the source term. Some isotopes are short-lived. Bromine 83, for instance, one day after shutdown, you don't find it at all. It is a very short-lived, 22.3 hours half-life, 32 minutes half-life. Krypton is a noble gas, so it doesn't affect the human body, doesn't interact chemically, so it's primarily a gamma ray emitter. It has a very slight health hazard. Iodine 131 is that one that we worry about. The boiling point is 185 degrees Celsius. So if the temperature of the accident of the fuel reaches 185 degrees Celsius, iodine usually at room temperature is a liquid. It's all a gas. It is released from to the environment. And that iodine, basically, most of the isotopes of iodine, as I show you here, come from tellurium 132. So the first radioactive isotope that is detected in a reactor accident is the tellurium 132, and then it becomes iodine 132, 134, 136. And we know that iodine is a seeker of our thyroid gland. So in that case, it concentrates in the thyroid. And in fact, some interesting aspect of the safety in the case of a reactor accident is to distribute potassium iodide pills. And the suggestion here is that the iodide goes to the thyroid gland in our neck. And if it goes and concentrates there, it prevents the radioactive iodine from getting to the thyroid gland. And in that case, we don't get the cancers or what they call thyroid nodules in the thyroid gland. The two main isotopes in that case, short term, is the iodine 131 and iodine 133. However, we also released long-term lived isotopes, strontium 90 and strontium 89. The concern is that strontium 90, 28 years half-life. A here is annum in Latin, so that's a year. And this is what gets into the human body and seeks the bones, because in the periodic table, strontium and calcium are in the same basically column in the so they have similar chemical properties. And then we also worry about the cesium 137 that has a 30-year half-life. It has an internal hazard to the whole body. But we know that cesium-137 is like potassium in the periodic table of the elements. So it has a biological half-life. The body, the kidneys are filters in our body. The liver eliminated. So really the main concern on a short term is the iodine isotopes that seek the thyroid gland and the strontium-90 that deposit themselves in the bones for a long term, for a lifetime, as a matter of fact. So here I show you the decay graphs for strontium-90 and cesium-137. I'm not showing here the fact that cesium-137, like potassium-40, is eliminated from the body and is not as harmful, I would say, or risky, like the same as in that case, the strontium-90 that seeks the bones and once in our body remains there. Interesting enough, each one of us here, if we are put through a whole body counter, we can detect some trace amounts of the strontium-90 in our body, and that remains from the testing of nuclear weapons in the atmosphere in the 1950s. So the fission products remained in the atmosphere and are still settling down to the ground. So if you get in the nuclear industry, the first thing they do is give you a whole body count, and the instrument is so sensitive that they can detect a very tiny amount of the strontium-90. This is a suggestion that in unit number 3, as I suggested, that even though the unit had its fuel outside the core, but it had a fuel storage pool. And this is a picture taken, in fact, by a group from our students here. I took them to the LaSalle plant, which is a boiling water reactor in LaSalle, Illinois. And this is the extent of the water storage pool that I've been telling you. The fuel in that case is stored in the pool, and they have a boral. Boral is boron carbide in a matrix of aluminum. So it's there to absorb the neutrons so that the pool does not become critical. But it has to be cooled. And you'll find that it produces steam at around 300 degrees Celsius. So it's a very high steam there produced from the pool. The fuel is left there for storage until it's taken out and then either reprocessed, like in the European countries, France, Switzerland, Sweden, Ukraine, and Russia, as well as Japan. In the United States, it's left there for 10 years until it cools down, the radioactivity goes down, pending a decision on whether to put it in a repository or simply place it in silos at the site of nuclear power plants. So the suggestion was that in the earthquake, that pool cooling disappeared, the fuel heated up, and that could explain the fire that happened in unit number 4. And in fact, this is a picture before the accident. Look at that yellow part here. This is a cap that covers the core itself. It suggests that the fuel was outside the core, but at some point, if you do not provide cooling, then the fuel would catch fire. Apparently, that's what happened in general. All right, so this is again the unit 1. The unit 1 had a unique design. It looked like the RBMK 1000 reactor. Is that it didn't use a steam generator, it used a steam drum, where the mixture of boiling water and liquid goes to a steam drum. The water is recirculated back to the core. It was the oldest unit built at the plant, so it had an older design, and the steam goes to the turbine plant. So the units even had differences in the design itself. I show you here the chronology of the accident, looking from the side of unit number 1, 2, 3, 4. 2 was not very much damaged, as you could see here, but the top of unit number 1 was really very seriously damaged. Number 3 was very badly damaged. 4 had apparently a fire with the core outside with the fuel outside the core of the plant. You could see here that the design of unit 2 and 3 doesn't use a steam drum like the unit number 1. So unit number 1 was a very old unit, probably built first. You see the steam drum here. In the case of the unit 2 and 3, they had a different design without the steam drum. So basically the steam mixture went, the steam went directly to the turbine. Again, they had the steam-driven turbo pumps rejecting the heat into the pressure suppression pool and the condensate storage tank. And those pumps were, of course, flooded. So they stopped operation. This is a picture from above units 1 and 2. This is unit 2 here. That's probably because the roof was not blown up. And the right is unit 2, unit 1. And you could see here, this is an infrared picture. So it shows the heat generation inside the plant. And notice that some of the ejecta, stuff that was ejected from the hydrogen explosion that I'll mention in a moment, were thrown on top of the turbine hall or the turbine building. So this is as a way to describe really the details of the accident. These are pictures of the fire in unit number 3 taken from the top. And it was very, very badly destroyed. You could see here the fire. Each unit had a different kind of sequence of events. This is what happened at unit number 4. And taken by unit 5 had a different sequence of events. And unit 6 also had a different unit of events. But most of them had hydrogen explosion, that hydrogen that was not released from the containment structure eventually reached a situation where it was reactive with air and had an explosion. These are the hydrogen explosions. Now I remind you that TEPCO, the Tokyo Electric Power Company, does not acknowledge that there was a steam explosion. The evidence, though, is different, and this is worthy of investigation if you get involved in the safety field. This is the unit 1. This is basically video grabs from a video by television screen. This is what happened at unit number 1. You could see here, this is identified as a hydrogen explosion. You could see the explosion basically propagating horizontally, and it has been associated with a depressurization when they couldn't release the hydrogen from the containment. Another explosion here is shown in unit number 3. However, unit number 3 is suspected to be a steam explosion. Let us look at the video here. It is not an explosion that happened horizontally. This is pictures of it. You could see that it happened higher than the stacks, all the way up to the sky here, and it went up really vertically to a great extent. And I took all those videos here for the gentleman for your own perspective. And notice here some of the debris falling down, and the ejecta went up 3 times, 1, 2, 3.5 times the height of the stacks in that case. That is very, very similar to what I have shown you earlier in the steam explosions in the borax experiments for boiling water reactors. You could see here how high the explosion went, how debris were thrown up in the sky and then fallen down. And this type of an accident has not, unfortunately, been studied. What we can think about is a model that happened in vortices generated in when some plants eject the pollen outside of their tips and spread their seeds in the environment. All right, in the same way as the 3 Mile Island, definitely there was a hydrogen explosion. And again, TEPCO doesn't tell us the whole story. There is a suspicion that the hydrogen generation itself could have been caused by the interaction between the steam and the very hot zirconium, similar to what happened in the SL one reactor. So we should go there and gain some inspiration from what happened there. Another issue that is still being debated is the use of the mixed oxide fuel. In Japan, I mentioned that one of the units had the mixed oxide, and it suggested that it is highly reactive in that case. The simulation that showed that the core basically leaked from the bottom of the reactor vessel, this would be the reactor vessel here, this would be the control rod, is that there is a little seal here. Do you see that seal that is made of graphite? That was not enough to contain the molten core from leaking through the bottom of the pressure vessel. So that is a design feature, a flaw that should be, of course, fixed in the existing boiling water reactors. And another interesting topic that needs to be researched thoroughly is, of course, the possibility of not using the core spray system of a certain temperature reached by the fuel, because in that case, you make the accident worse by generating the hydrogen in that case. At the Fukushima accident, some fires did occur at the transformers here at another plant, Oganawa plant, but it did not reach the level of seriousness that was attained at the Fukushima plant itself. And in the same way as Chernobyl, where the site has been enclosed into a large silo, Japan has been building silos. These are in the stage of construction around each one of the plants. And of course, lots of the water that was used in cooling has been stored, and then now it's being released to the Pacific Ocean. One last item that I want to mention to you is that we have learned from that accident that happened in March and prevented an accident that could have happened in the United States in June, when one of the reactors on the Mississippi River, in fact, started being flooded. And that is a Cooper Station flooding that happened in 1993. You could see here the plant along the shore of the Mississippi River, but the other plant is the Fort Calhoun flooding event. You could see here in June of the same year, the Mississippi started flooding, and you could see the plant here totally enclosed in water. They used some kind of a rubber kind of a shield to keep the water from the same equipment. And somehow the lesson has been learned from Fukushima in preventing a major accident a few months later, 3 months later, at Fort Calhoun. Eventually that plant by the utility was simply decommissioned, and the utility does not want to deal with the problem of dealing with the possibility of an explosion. Right now, as you could see, the water has been stored. The radioactivity has been calmed down. They're trying to release it to the rest of the environment. You could see here the top of unit number 2 removed. That was because that unit was basically not operational. And basically the radiation risk was such that nobody was affected in Tokyo. And that is a neat thing that happened to us. Earthquakes are a way of life in Japan, occurring every almost 5 minutes on average. Structures are built to withstand Earth's movement. And basically the society there has lived with it, even with the case of tsunamis affecting the fishing industry. And I would like to just finish here by quoting Professor Lester from MIT. He says, in historical terms, that puts the field of nuclear engineering today roughly where electrical engineering was in the 1900s. The creation of the electric power grid, television, and telecommunication could not have been anticipated by the electrical engineers of the year 1900. Likewise, no one today can foresee the future of nuclear energy technology. All that can be said with confidence now is that the nuclear power plants of the year 2100 will have about as much resemblance to today's as a modern automobile has to a 1911 Model T, Ford Model T. New materials and systems are being developed all the time to make nuclear safer. The need for intellectual vitality, flexibility, and creativity has never been greater, and our small group of people are there to be part of it. And I wish you a nice afternoon. Thank you for your attention.